Hello everyone, my name is Yi Li. I'm the PhD student in Space Lab in NJIT. I would like to introduce my supervisor, Dr. Shaohua Wang, and our collaborator, Dr. Tin Yuan. Today, my topic is for localization with code coverage representation learning. In the software development, testing process is an important step to evaluate the quality of the software. And in the testing process, the developers often run the test cases to check if they can fail or pass. And each test cases will execute different statements inside of the project. By collecting all the information that including the execute, not execute, and if the test cases pass or fail together, we have a matrix called code coverage matrix. In software engineering, using this matrix to locate where the faults inside of the project, we call this whole step is for localization. There are many state-of-the-art for localization approaches. They all belong to three main types, including the spectrum-based for localization, mutation-based for localization, and machine learning or deep learning-based for localization. As for the spectrum-based for localization, they often directly use the formula to calculating the score based on the code coverage matrix. The score is higher means the statement is more likely to be buggy, but they have the key limitation that this kind of approach may provide the same score for many statements at the same time. For example, the OCHIA, which is the most famous spectrum-based for localization approach, they use this formula to calculate the score. In this example, for statement 2, the failed test case is test case 2, and the passed test case is test case n, and the test case 1 is not executed, so we're not counting this formula. As for mutation-based for localization, we first of all apply a mutator on the original source code, and then run the spectrum-based approach on the source code with mutator. By checking the different score with different mutators, we can locate the bug. The limitation of this kind of approach is that they cannot deal with the bugs that requires the fix that more complex than a mutator. For example, if we have some source code like this, then we will have different mutators to mutate a statement. As for the machine learning or deep learning based for localization, they may directly use the spectrum-based and mutation-based results as features for the model to learn the score for the photo localization, but they have the key limitation that because they directly use the spectrum and mutation-based results, so they have the similar limitation as the two approaches. To overcome the limitation in the existing three kind of approaches, we come up with our approaches called DeepRL4FL. Here are some key ideas for our approach. So first of all, because our approach is dealing with the code coverage matrix, so we regard our problem as an image processing problem. In order to make the model can catch more information from the matrix, we're doing the reordering to reorder some test cases to group the useful information together. And also, in order to analyze the relationship between different statements, we consider the statement dependencies. And by combining together the code coverage matrix, statement dependencies, and original source code content together, we can have the final for localization score to do the for localization. In the key ideas, the most important thing is that how we enhance the code coverage matrix and how we do the reordering. As for a original code coverage metric, the spectrum-based and mutation-based approaches will replace the execute as 1, not execute as 0. But this metric has a big limitation that information about statement coverage and the test case fail or pass are separated. To putting this information together, we collect the error message, get from the failed test cases, and go through the whole error message and find which statement in which test cases failed. Then we directly replace that one as -1 as shown in the red part. So in this case, we can use a matrix containing the 1, 0, and the -1, including both the code statement coverage information and the test fail or pass information. As for the reordering, the original code coverage matrix 0, 1, and -1 are randomly distributed, so it's hard for a model to directly learn the information from it. In order to let the model catch more information, we doing the reordering on the test cases. We put the test cases with the most -1 on the top, and then based on number of 1 to rank the test cases. In a real example, as you can see in the left figure, the original test case running results is like this. most test cases provides result 0, and only a few test cases are useful, so that you see that they distributed here. And after reordering, our approach will group the useful information together at the most left part, so you will see all the test cases running pass or fail will all collected in this area, and the graph model can easily catch the useful information from this part. By having these key ideas, we come up with our approach DeepRL for FL. Here's the overview of our approach. Firstly, by having the test cases and the source code, we directly generated a code coverage matrix, and then we do the enhancing and reordering on the top of the matrix. The next step is that we collect the statement dependency information and apply this information on top of the code coverage matrix to do the code coverage representation learning. And then based on our original source code, we generated abstract syntax tree, and we do the code representation learning on this trees to catch the tree structure and the tree content. In the end, by combining all the information from these three main steps, we do the localization for the statements and methods. By having our approach, we do the empirical evaluation on the performance of our approach. Due to the space limit, here we're mainly focusing on the statement level and the method level for localization, but we also do the detailed analysis on the influence for different features in our approach. If you're interested in it, you can refer back to a paper about RQ3, 4, 5, and 6. As for the dataset we used in the evaluation, we used the defects4j that contains 395 bugs from 6 open source repositories. And then we use the recall at the top 1, top 3, top 5 mean average ranking and mean first ranking as the evaluation metrics to do the evaluation. As for the evaluation, the RQ1 statement level for localization comparison, the results shown in this table. From this table, we can see that our approach can always perform better than all the baselines on top 1, top 3, and top 5. As a summary, our DeepRL for FL can locate at least 32, 14, 13 more bugs comparing with baselines at top 1, top 3, top 5 at statement level. And for the RQ2 method level for localization comparison, the results shown here. From this table, you can also see that on top 1, top 3, and top 5, our approach can always perform better than the baselines. As a summary, the DeepRL for FL can locate at least 32, 12, 6 more bugs comparing with the baselines at top 1, top 3, and top 5 at method level. By having the results like this, we already know that our approach can outperform all the baselines, but we still want to use an example to show the contribution of each feature inside of our approach. For a given project, if our approach without the reordering and the statement dependency, we can only run the buggy method in top 5. But if we have the reordering or we have the statement dependency, we can rank them at the top 2 or top 3. If we have both of them, we can rank the buggy method in top 1. It proves that each feature inside of our approach can contribute to the final results. And if we adding them one by one, the result will improve. After we talk about the example, we want to make a summary for today's presentation. In today's presentation, we firstly talk about what is the localization, and then we introduce our new approach called DeepRL for FL with some key ideas. And then we introduced overview of our approach. And after having our approach, we analyze the results. The results shows that our approach can outperform all baselines. It means that our research is success and meaningful. So this is all the presentation today I have. If you have any question, please ask. Thank you.
Okay, hello everybody, and welcome to this session about fault localization. We have two authors, Tin and Yi, who I would like first of all to thank for their presentation, and they're here to answer your questions. So please write on the chat that you can find on your right side. Please write your questions so that I can pose to them your own question. Meanwhile, we can start with my questions. So I see that you have provided a technique to localize fault at the method level and at the line level somehow. So my question is, and it provided very good results. So if you would have to speculate about your result, do you think there is any context where this approach will be particularly accurate, and other contexts where the approach will be particularly inaccurate.
So yeah, I don't know where E, but the idea of treating um, uh, the coverage as an image and leverage the capability of recognizing the pattern of the buggy is pretty much dependent on how the coverage to be diverse. So in this case, if you having the test case that run it's quite diverse, give you cover more statement and you have more pass fail tests, then the result usually to be better. But if you having the test cases that cover just one part of the code coverage, which means that the information on the test coverage matrix is very uniform, it's not quite diverse, then the result would not be very strong.
Mm-hmm. Very
Yeah.
interesting. So, similar to that question, while waiting other questions from the audience, I have a similar question, and it will be, would the approach scale in industry? I mean, what would we need to be done so that the approach would work in an industrial environment somehow? Or do you think that it could be used as is?
I think that to make it scale, we haven't tried in the industrial setting yet. But if we want to make it scale for industry data set, the thing that's more interesting is actually the time consuming is not on the training, but actually on the testing and validation
Uh-huh.
for uh, for the for the detection. So that's why if we can improve that part, the whole process will be better. So in other words, the training data and things does not really much require heavy computation, but the validation also. Yeah.
Mm-hmm. Nice. Uh, so now, can you elaborate a little? Still waiting for questions from the audience, so I can still provide mine. I don't know if Yi or here we have the first question from Guru, and who says, "Nice piece of work. What type of techniques have you used for filtering the dataset?"
Go ahead, E.
Yeah. Uh, for the data set, we used a well collected and cleaned data set called the defects4j. That one is an existing work and collected and filtered already by several professional developers, and they think that the bugs they collected inside all uh, very good data, or the bug is very clean, so the developers can directly see what actually the bug is, and they also have the true labels. So our work is directly built on the top of that data set. We didn't do the filtering actually. Yeah.
Mm-hmm. Very nice. So no filtering on the dataset, since this was already well established dataset in the literature. While waiting for other questions, my question is if you can describe somehow what to do next. So now that we know that, if you can elaborate a little bit on future works. So now that we know that this technique works, how to make it better, more accurate, more faster. I don't know.
Yeah. So currently our work is currently based on the spectrum-based and mutation-based existing techniques. The most time-consuming thing, I think Tim just mentioned, is running the test case to do the validation. So this is the necessary process for both the spectrum and the mutation-based approaches, and even for mutation one, they may try different mutators and run several times, so it's really takes a lot of time. The next step, we are considering to do the full localization on maybe without or with less efforts on this part. So in this case, we want to achieve similar goal, but to the less time cost. This is
Uh-huh.
one direction. Yeah. The
Uh-huh.
other direction is that currently the full localization just provide you a one statement, showing that one statement is buggy, or 1 or 2 precision is buggy, but they will not say. But in the real world, you will see that when there is a bug, they may fix several statements at the same time. For example, a if statement with all the statement inside, something like that. So the next step we are considering, maybe we do the for localization to provide more precisions just than one statement. Then the developer has more clearly about which statements really need to be fixed together at the same time. Yeah. Thank you.
The question I have is that it seems that your approach is independent from the programming language.
Yeah.
But would you think that this is really the case? There is really no programming language like Python or I don't know, where your approach cannot work on? That's the question.
Okay, thank you. So our work, the information from our work mainly from the 4 parts. The spectrum and mutation running results. This is really based on the test case running results. It's not really about the programming language. So it's not depending on any programming language. The third part is the source code itself. But if we change the data to the other parts, we can also use the other source code to train. So it's also fine. Then the last part is the error message, which is when run the test cases, it will report something crashed. So this one on different programming language may be different. Then the strategy on this thing maybe has a little bit changes for different programming language. But overall, I think it should work on all programming languages.
So the framework as a whole is independent. Okay.
Yeah, so
Yes.
a little bit more is that so we're relying on the test coverage. So whatever language you use, the test coverage is still, test coverage. What line have been covered, and what statement what test would be pass or fail. The second part we rely on the dependency between statement. That's the notion that the dependency between statement also independent of the language itself. So you can depend on different language, you will use different program dependencies for different statement in that language. Then the final part would be the code. The code and the code itself is just code, whether code buggy, Python code, C code, Java code buggy. We learn from that, and that's also language independent when we learn about it. Yeah.
So we have a question from Alex. The question is, have you considered information from the version history? Like, for instance, knowing that a certain state all tests passed and thus only changed lines can have introduced the bug.
Yes, this
interesting direction. Yeah, that's quite interesting direction. We have not looking at the change status of the line, but we want to consider that when we do more like debugging or formalization from version to version. That information that Alex suggests is quite useful.
Yeah.
In that case, I think the chain and the approach would be the metrics that we build from test coverage will need to be modified incrementally. Incrementally mean so when you certain line of chain, we eliminate other line out of the image that we build from the test coverage. Yeah.
Okay, so we have only 30 seconds remaining. So instead of being cutting off, I suggest that who is interested, like Guru, with another question, that we move now to the discussion room. And so I thank Tien and Yi for the presentation and for the answer, and then I encourage everybody who is interested to talk with them to move to the discussion room so that we don't have time limits. Thank you again. Bye-bye.
Thank you. Thanks so much, David. Nice to meet you. Yeah. Bye.